This is David Johnson, and today I would like to talk about composite material properties and correction factors. And today I'm just going to concentrate on the ply-by-ply properties. In other words, the Lamina analysis method technique rather than the Laminate. So these properties I'm going to open now, which is created by Collier, are really for use on a Lamina analysis. And this is the orthotropic form with the material properties. I'm going to go over this pretty quick. Material properties can be a pretty complex topic, a lot of testing. I did a lot of work at Goodrich, and what I figured out at the end of the day is I don't think there's any aerospace company in the world that's got all of this figured out, but you come up with a methodology, you create your allowables, and you certify them, and hopefully the FAA buys them off. So this is a graphite epoxy. This is fabric. We can have a specification in here. The density, obviously we use this density to calculate the weight. We have the thickness per ply. There's a buckling KD, not quite sure what that one's used for. Bending factor. Composites have this unusual property in the fact that if you use the axial capability and tension compression for the bending calc, you'll find out that you underestimate the bending strength. So we have a bending correction factor when we have a pure bending moment on a solid laminate. And right now we've got 1.3. I think Lockyer uses something around 1.3, but this could be very material dependent. We have the fiber volume and the glass transition, just for reference. This was not being entered. And probably very important, which I've not discussed, is a FEM material ID. So when you create your FEM, your wing FEM or your fuselage, and you want to import into Hypersizer, it's very, very important that you use the material ID that's in this box. Then we have the temperatures. Collier's only put the temperature in for 72 degrees. We should have something really from minus 67 or minus 75, depends on where you work, all the way up to 250 degrees or maybe 350 degrees. And what Collier does is they interpolate linear between each of the points you put in. So if you've got a curved allowable curve for temperature, you need to put in quite a few points in here to capture the curve. Otherwise, let's say I put minus 67 and 250 degree properties, it will just draw a straight line between those two properties. So today he's only got 72. I'll give you one warning, is when you put in your analysis that you want to do analysis at 250, Hypersizer doesn't warn you in any way whatsoever that you're still using 72 degree properties. I think there should be a warning to say you've put in a temperature outside the capability of the material that the data's been entered here. So very quickly go over these. We have stiffness. So obviously tension, compression and shear, all very straightforward. What's pretty cool about Hypersizer up here, you can click on SI and all these units change from gigapascals to MSI. I think that's kind of cool, especially for people that are working in unusual units. But of course here we're in the United States, so we're using MSI. We have stress allowables in KSI, and we have strain allowables. Now obviously these must coincide, and one thing that becomes very evident, and we'll show later, is that these allowables are pristine allowables. There's no correction factors, there's no damage. This is just plain fabric or tape or a hybrid, and we have some properties. Puck factors, not sure that's really too relevant. We have effective laminates. We haven't set any up here. We have laminate allowables is included in this form, but we're not doing a laminate allowables today. And we have thermal properties. Obviously the coefficient of expansion for graphite is very low, but sometimes you want to still do the thermal analysis. We also have joints and holes, so you won't want to put in your characteristic distances. And I forgot what these are used for, but generally we don't use these in the analysis. I think perhaps this is used, oh, I'm not going to say because I can't remember now. And we have some out-of-plane laminar allowables. These are very important. The issue is where do you use them in the analysis? Hypersizer does do a little bit of out-of-plane analysis, but you need to be careful with how you use these. But these properties are very important when you're doing composite design. Now, if we go to the important form, so those are what I call the pristine allowables. So it's just filling out the allowables table. It's quite a lot of data there. You need to do quite a lot of tests just to get those allowables. I think Goodrich did something like 4,000 coupons just to get to that point. Kind of stunning, really, but it's an expensive proposition doing this. So this is the correction factor form, and I'm just going to skim over this because we could spend probably a week talking about this, but the bottom line is these are the pristine allowables that you entered in those forms that I just showed. I think actually those forms could be a lot clearer. I think there's, at least my view is, it needs to be reformulated and made a lot easier to read, but that's a minor point. But anyway, this is more of a better summary of all those tabs we've just looked at. So these are what we call our uncorrected values, and we have stiffness, stress, strain, and some bolted joint stuff. And I'm just going to go over the correction factors that we might use. And most companies won't use all of these, but Collier had to put all these corrections in to accommodate what all corporations might do. So we have a laminate correction factor, which I'll probably have to talk about later. BVID, barely visible impact damage, is probably by far your biggest correction for the stress and strain allowables. You can see here a big correction, 60% reduction. Now there's an irony here in the fact that we're applying corrections to a layer, effectively a layer, not really a laminate, but unfortunately this is the way the analysis is set up. This is what most corporations do. So barely visible impact damage, you must correct your stresses and strains. You notice that the stiffness has not been corrected. On a global perspective, really the stiffness is not really corrected. Then we have a co-cure. We don't have anything in here, but we should have, so this means that this collar allowable couldn't accommodate a co-cured lamina. So if we had a honeycomb structure with a co-cured skin, this particular allowable wouldn't be any good. But co-cure corrections can be pretty significant because when you put the pressure on the co-cured side, you end up with like a golf ball effect, a dimpling, and so it bends all the fibers. And it reduces the allowables by quite a significant amount. Then there's thickness corrections, and what we find is if I test a very thick laminate, say 1/2 inch, or I test a very thin laminate, 0.40, I may end up with a different allowable and even a different stiffness. It's all to do with the manufacturing process. So there's a thickness correction here. There's a residual strength correction. The FAA rules state that your allowables must really be allowables that take into account time. And so residual strength means, what would my allowable be after 30 years of graphite in service? If you have metallics, it's the same property. For composites, we get a degradation of around 5 to 10%. Most North American companies conveniently just ignore this figure and just use what I call not aged. In other words, it's the allowable after I've just cured the laminate. I go test it. There's no 30 years. Of course, we can't easily get this number, but there is some testing around to show that this can be kind of a 5 to 10% correction. AFP, that's a manufacturing process, and it's automated fiber placement, usually used for large flat structures. We try to put down a lot of plies all in one go, but there's some pretty significant issues with this process, and we end up with lower allowables. So there's a weight penalty to using this AFP process, which a lot of people don't really recognize. But also there's a significant correction factor, and it can be for all stiffness, strength, and strain allowables. NPT, This is where we drill lots of holes for perforation. This is pretty much used in the cells. This is where I use this at Goodrich. If I drill lots of holes in the laminate, I get a pretty big correction, and if I drill the holes afterwards and drill through the fibre, I'm going to get a lot bigger correction than you say using the Boeing method where they use the pin, lay upon the pin tool. So this can be a very big correction too. We have aging and fluids, which sometimes are used and sometimes not. Now you can see that that's kind of a bit of a nightmare in the fact that that's a lot of data, and you have to do many thousands of coupons to get all these correction factors, and there's different ways of doing this. But this is a topic in itself. I can't go into that here, it's way too complicated. But I'm just trying to give you a heads up of, if you have any laminates with these issues, you have to use a correction factor. And we put in a tool here to put in some thicknesses and say some laminates, because for each different laminate these corrections can be different. So just for example, I'm not quite sure why this is not plotting up. I guess I'm missing something here. I'll have to go back to that. But normally we can plot up the laminate. So what happens is these are the corrected values. So when we do our analysis, the ply-by-ply analysis, and we look at the 0, 45 and 90 degree directions for each ply, these are the allowables that are used. And notice here, we say this strain allowable for let's go to compression. These don't look really very correct. This is just something that Collier's put in, but I don't think these are correct. For instance, the ETU at 5,000 looks pretty good, but the ECU, we're usually kind of down in the 3,500 microstrain, 4,000. Of course, it depends what type of material they use, but we get low allowables. So this is why a lot of people that are new to the topic, they go do some analysis and they use these pristine values and have no understanding of certification of aeroplanes and what we're supposed to do. And I've been on many programs where I've come along a year after the start and a bunch of stress engineers are using these pristine allowables. Well, unfortunately that's not correct. And even for secondary structures, we need to take into account all of these manufacturing processes and make corrections. A very, very quick overview, but thanks for listening, and have a good day. Thank you.